right, we'll give it just a minute, Coogan, before we get started, just to let StreamYard do its thing and let everybody get in here. While
Sounds
everybody's
good.
filtering in, if you want to drop in the chat where you're from, I always love seeing that, seeing where everybody's from. And that way I know people are alive and can actually chat with us too. But while we wait for that, yeah, I guess I'll start by saying thanks for doing this with me, Coogan. We're going to be talking about zkSync and deploying your first smart contract. I don't know, Coogan, if you want to introduce yourself a little bit, tell us a little bit about you.
Sure, absolutely. My name is Coogan Brennan. I am head of education at Matter Labs. Before that, I worked at Consensus Academy for about 5 years, ran the boot camp and did technical trainings. And yeah, I'm based on the East Coast of the US. Happy to be here. Thanks to Chainlink for having us and excited to onboard folks to zkSync today.
Awesome. Thank you. And I'm Richard Gottlieb. I'm one of the developer advocates at Chainlink Labs. And yeah, I'm based in Texas where the weather is cold and hot depending on the day and time of year. It's cold today. It was hot yesterday. But yeah, I saw somebody's from San Antonio. So I'm a little bit further north up in Dallas. But yeah, looks like everybody is from all over the place. We've got Africa, San Antonio, Chicago, Alabama, Estonia. Wow. Arkansas. I think that's the first person I've ever seen from Arkansas on one of these. So awesome. But yeah, Coogan, I don't know. Do you want to get started telling us about zkSync? What the heck is zkSync? And why is it
Sure.
awesome?
Absolutely. So, welcome everybody to our live stream. Very excited about this. We'll definitely be watching the chat throughout. So, if folks, just popping questions, very, very casual. It's Richard and I just hanging out. zkSync. So, people know about blockchain, right? People know Bitcoin and Ethereum. I'm assuming people are talking about the link price. So, I assume you know what Ethereum is. And essentially, blockchains such as Ethereum and Bitcoin were in some ways proof of concept that certain ideas were correct. So the idea of the Bitcoin white paper and later the Ethereum yellow paper was to be able to provide permissionless settlement layer, sort of a transaction layer for financial payments, and then with Ethereum, more general computation. So that was considered to be wild, in the late 2000s, 2010s. And for a long time, people were saying this was not going to happen. This was not going to be. This is not going to be a realistic project, and this is magic money, and it's just going to disappear all day, tomorrow. That did not happen, right? The network continued to grow and build, did not break. Other networks kind of rose and fall, but those two have continued to be very prominent, as well as other awesome networks. However, even though that sort of proof of concept has stood the test of time, we're now seeing that it's not necessarily production ready. And what I mean by that is a few things. What people are bring up typically is transaction throughput, the amount of transactions that a network can process simultaneously, as well as cost of transactions. So Ethereum averages around 15 transactions per second, and the gas prices, as folks know, can fluctuates wildly, but essentially it can be I love this chat. It's a good chat. The fees are also very high. So you can pay for the ERC20 transfer, you can pay $1.50 or $2, which isn't necessarily a large amount, but in the context of sending $1, you can pay a lot in fees. So the question becomes for Ethereum in particular, how do we provide scalability without sacrificing the principles that brought us to this place? The proof of concept showed the importance of decentralization and distributed networks and cryptography, that sort of thing. So what Vitalik and other all-core devs have proposed is this idea of a roll-up centric future roadmap for Ethereum, so that Ethereum scaling in terms of increasing transaction throughput from 15 today to hundreds to possibly thousands of transactions per second, and lowering the costs from what was $1, or $2 for a transaction to sub-cent and sort of less than that. Those solutions are going to be found on what are called layer twos. And so what layer twos are essentially networks that take transactions, compress transactions, and then verify a number of transactions on Ethereum. And the analogy that I've heard a lot that I like is buying a gift card for a shop. So let's say you buy a gift card for, I don't know, somebody in the chat. I'm trying to think about, I guess, let's say for what's the gas station in Texas that everyone was the chipmunk in
It's
it?
Bucky's.
Bucky's. Let's say you buy a Bucky's gift card, and I send it to Richard, and Richard is able to go to the Bucky's in where'd you say you were? Dallas, or
Yeah.
maybe outside of San Antonio, or maybe all the way in Las Cruces. Bucky's, there we go. And you're going around and you're using that Bucky's card, right? And you're essentially transacting on this sort of Bucky's network, you can sort of say. And if you needed to, you could cash out that card at a Bucky's, but for just sort of ease of use, you're going to go to different Bucky's, and that provides on the Bucky's side, it actually provides them to do. Let me make sure if you guys can still hear me. The transaction fees, a store has to pay their, they do pay a vendor fee for sort of point of sale transactions, which typically are sort of hidden in the prices. But so a gift card sort of prevents that. And then at any time, you can always cash it out, assuming that there has been sort of a proper sort of tracking of fees. But we all know Bucky's is an upright organization and, a community steward. So of course they would, right? So layer twos provide a similar sort of path to scalability for Ethereum, where essentially what L2s provide is that you lock up a certain amount of funds on Ethereum, which allows you to bridge them over to an L2. Some of the popular L2s are Optimism, Arbitrum, zkSync, which is what Meta Labs runs. Base is another one. What are some other ones, Richard, that I'm forgetting? We can all look up an L2 beat. Linea, Scroll. These are all L2s.
Yeah.
And what they do is essentially.
Ones I know of.
Which one? Yeah.
I think you've hit most of the big ones I know of that come to mind.
And so Polygon, yeah, exactly. So Polygon zkVM, right? Because Polygon POS is technically a side chain. Yep. Okay. So what we do is you bridge funds to this L2s. You transact on the L2s. The fees right now are extremely low because of 4844, the Denkun upgrade that just happened on Ethereum. So we now have sub 1 cent transactions for ERC20s, and which is excellent and is huge and really exciting. There's also a throughput. We hit 188 transactions per second back in December during the inscription phase, which is currently the sort of the all-time high, the record to beat, including for Ethereum, for a sort of a major public network. And so we're getting these sorts of advancements. But someone mentioned Polygon. What's the difference between an L2 and a sidechain? So what makes an L2 different is that an L2, within that bridge contract that we talked about where you lock up your funds, there's a certain amount of smart contract logic that in case there's any sort of issue on the L2 network, that you can permissionlessly and just using L1 transactions, pull your funds back out of the L2. And so there's a really big difference there between a side chain. Someone's asking about the difference between side chain and L2s. There's between a side chain, which are really important, but like Gnosis chain is a side chain, Polygon is a side chain where you're essentially locking up funds and then you're moving it over to a separate consensus layer, separate nodes, separate executions, that sort of thing. And then you bridge it back over. There's sort of like a trust layer with side chains. L2s try their best to what's the word, kind of abstract away that trust factor and to make it more sort of rooted in L1. So the reason why they're called layer twos is the impression is that Ethereum is the layer one. They're also Bitcoin L2s, which are also very interesting, where they use Bitcoin as a settlement layer. But essentially what it is that you're quote unquote inheriting the security properties of Ethereum by allowing people to exit on Ethereum, assuming that a sequencer goes down on the L2, some sort of network outage happens, or there's some sort of network corruption, whether that corruption is like malicious or just inadvertent through a bug or something. So that's sort of the value proposition for L2s. As you can imagine, there's a huge design space to implement these L2s. There's two broad categories. One is an optimistic rollup. The other is what's called a zk rollup. And the biggest optimistic rollup is Optimism. No surprise there. And Optimism L2s work through their sort of security, their way of using, finding their L1 security layer is through what are called fraud proofs. Optimism prefers the term fault proof, but the common term is fraud proof, where essentially there's a sort of a game theoretic mechanism that is people watching for malfeasance or malicious transactions. And if they find one, that they can post what's called a fraud proof on Ethereum. And Optimism has actually just activated permissionless fraud proofs on Gurley right now, or Sepolia, excuse me. And they're hoping to do that in their network in the end of the summer. That's what they say. So that's one way. But a lot of people have recognized that there's a number of issues with optimistic security mechanisms. So, for example, there's a long lockup period. Like you have to wait a certain amount of time, about 7 days, for your funds to be available on L1. That's if I'm sending Richard some DAI on Optimism to compensate him for my Bucky's memorabilia that he bought for me. If I'm using the cheap fees on Optimism and I send those to Richard, even if MetaMask says those funds are confirmed on Optimism, it'll take Richard a week to take those funds back over to Ethereum and unlock them. They're still safe. They're still there. It just takes a little bit longer. And that's always probably going to be a part of the Optimism design, regardless of technical advancements. It's just sort of part of the security mechanism. zk's, on the other hand, are using a different security mechanisms called zero knowledge proofs. And someone mentioned that they don't know anything about, they have zero knowledge about zero knowledge proofs, which is a great pun. But you actually do know a zero knowledge proof. And I'll just do a brief aside. Also, Richard, if I'm just sort of rambling on, feel free to jump in. And
I think this is fantastic.
Okay, great. Wonderful. So people think they don't know what a zero knowledge proof is, but let me ask you, friend, let me see who commented zero knowledge. I'll call them out. Let me tell you, friend, whose name is I might have met zero knowledge. C Scrivo. Let me ask you, friend, do you know anything about digital signatures? Do you know anything about a wallet that holds private keys? Well, if that's the case, there he is. I see him right there in the chat. All right. So you used signatures on Ethereum, correct? Now, there's a little bit crypto 101, so I apologize. But when you make a signature, right, on an Ethereum transaction or a Bitcoin transaction or whatever transaction, essentially a cryptographic signature, what you are saying is I'm in possession of a private key that is associated with a public address, but you don't actually reveal anything about that private key. That's sort of the whole point, right? Is that there's a public form of information, your public address, that's associated with your private key. We can talk about unsigning in maybe another session. And so there is a zero knowledge proof there in the sense that that cryptographic signature implies a piece of knowledge, the private key, without revealing anything about that piece of knowledge, the private, right? So it's impossible to kind of reverse engineer a private key from your public encryption scheme in a quantum, in a non-quantum world. So that's what zero knowledge proofs are. Is essentially you can think about it 2 ways. One is a sort of privacy element, which is what we just talked about with digital signatures. But there's also this kind of knock-on effect of compression, data compression that happens, where zero knowledge proofs, when they get expanded out a little bit more from digital signatures, not only can they represent a private key that someone is holding, but it actually can illustrate a whole execution trace. Now, what is that? That sounds like a very fancy phrase. Execution trace is essentially the steps that a program needs to go through to achieve a certain state. So if I say 1 + 1 = 2, and I put that in the computer, depending on the programming, this is just sort of non-crypto, just CS, basic CS stuff, right? You put on a 1, and then you put on another 1, and then you put on add on top, and then you read it out. You say add 1, 1, and then you get 2 or whatever. That might not be actually how it works, but you guys understand what I'm talking about. That trace of doing that add 1, 1 can also be now verified using zero knowledge proof technology. It's sort of, it's a broad field, but it's captured a lot of it's grown a significant amount in the past 10 years. And so now it can capture larger pieces of information and kind of like larger designs of information. And so again, I understand there's a lot of technical discussions there, but there are two. A good analogy, I love a good analogy, is that digital signatures are to zero knowledge proofs what Bitcoin is to Ethereum, right? So Bitcoin is initially can do a lot more than this, but just for effective purposes here, it just sends, I'm sending one transaction, a certain amount of money to Richard or Mr. Scrivo in the chat. Bitcoin is able to do that very, very well. To do more advanced computation, that's where Ethereum comes in, being able to do Turing complete computer code, all these sorts of things, right? It's sort of an advancement of the premise of Bitcoin, which is this permissionless digital signature based payment layer, to a general computation permissionless settlement layer, payment layer, whatever. Same thing with digital signatures versus zero knowledge proofs. Digital signatures are, like we just talked about, confirming a certain piece of data, right? And it's doing it in a way that doesn't reveal anything about that data, the private key in this case. Zero knowledge proofs expand out that knowledge that's captured within the digital signature, so that, for example, okay, so I'll stop there. Any questions, Mr. Scriva? Did you get that about the zero knowledge proof and the digital signature? I'm happy to clarify before I go off on another tangent. All right, I'll take your silence as assent. So okay, so last little bit of information, which is that zero knowledge proofs, since they can capture all this information, there's a certain amount of data compression that happens there. And why is that interesting? Well, it's interesting because currently now, if you wanted to run a node on Ethereum and you wanted to validate the state, which is the promise of these permissionless decentralized networks, right? I can download, I can download Geth, and I can download Prism, and I can sort of download the state, and I can take transactions and I can process them, and I can say, yes, this is correct. To actually get to that, the different states that are implied by each block, meaning to be able to accurately compute the network state after each set of transactions comes through and is mined by the network, I need to actually run all those transactions on my computer. So I need to sort of say there's 10 transactions here. Richard has told me that the end balance is going to be this set of balances, but just to double check, right? Because we are not trusting, we are verifying. I'm going to go through and I'm going to just sort of go bop, 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 run all 10 transactions. Yep, that checks out. No problem. And I pass along the block. So the sort of, I've always really liked the sort of notion that state transitions are an emergent property of blockchains. Like, they come from more and more miners agreeing, or validators in the case of Ethereum, agreeing that a certain block has been correctly processed. That's why people sort of recommend you wait on Ethereum 7 or 8 blocks or 12 blocks, whatever your comfort is, just to make sure that the network has agreed that that is the network state on your block, which is T minus 12 in terms of blocks. Not necessarily because there's going to be a malicious transaction, but some people might reorder transactions, might do them a little bit differently, and it's fairly rare, but it does happen occasionally on Ethereum where it gets reorged and doesn't really matter too much. But anyways, that's sort of the point. So that is the current way to compute state on Ethereum, is to do this transaction processing manual, right? Very labor intensive. Anybody who's tried to sync an Ethereum node, it's actually quite hard. And it's quite hard in a way that's unusual for modern computing. It's hard on your input and output, because these are all great questions, by the way, in the chat. We're definitely going to deploy a smart contract in Remix with MetaMask. And we're going to do zkSync as well. I'll also address the quantum computing one really quick. And I got to move a little bit quicker, so I apologize. Essentially, zero knowledge proofs of the kind that Matter Labs, my company, develops, and that other companies in the space, like Linnea from Consensus does, or Scroll, or Polygon, are creating these worlds, these sort of huge circuits that are able to process Ethereum blocks and generate a proof which validates the execution traits for that block. So rather than having to go through and go bop, 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 instead, we can give a hash. Richard can compute it, produce a single hash, which is different than a digital signature. It's not only validating that a certain person holds a key, it's actually validating the entire execution trace of that block. And so that becomes incredibly powerful over time. So that's a long way of saying we use data compression from zero knowledge proofs, and zero knowledge proofs are, we have this meme that we like to say that has caught on very well, which is ZK is the end game. Because what's really exciting about zkSync, specifically the way that we're doing it, is the proof system that we are developing and have developed is so powerful that ideally Ethereum itself would sort of inherit this process. Like there's active discussions and sort of a way in which as this research becomes more mature, Ethereum will adopt it as its own process, because it's just a more effective way to maintain decentralization. It'll make running clients significantly lower computation. There's certain sort of trust elements that need to be increased. Like you need to trust the circuit construction, which is very challenging to understand. So we can get into all that. So yeah. So anyways, that is a huge discussion. But essentially, zkSync is a zk EVM rollup. So it's the L2 using zero knowledge proofs. That's what the zk EVM, zero knowledge EVM. We're not using it for privacy though. We're using it for data compression, just like everybody else on the network. So that's the value proposition, is that from that the zero knowledge proofs, we get a lot of really powerful abilities. Transactions become a lot cheaper. We can put a lot of transactions, more transactions in a block. And we're doing it in a way that maintains the integrity, the cryptographic integrity of the network. Because you can put a lot of transactions on a single chain. A lot of networks will advertise a really high transaction throughput. However, typically those are from you're making trade-offs in terms of you're creating more centralization within the network, that sort of thing. And then one quick question before we go into the workshop stage of it. Someone asked earlier about quantum resistance and quantum computing. So that is a concern just generally, and we don't have to get into the details of it, but essentially modern day encryption, just broadly speaking, not just for crypto, but just for banks, for any sort of use of wherever digital signatures are used, which is, if you're using the internet, use it every day, because HTTPS is the encrypted version of HTTP. That's essentially the default on all networks. So whenever you're browsing the internet, you're using encryption. There is a really strong chance. So the math behind that essentially assumes a certain amount of computing power that's available to process and sort of try to crack a code. And the sort of the science behind this new field of quantum computing suggests that there will be a massive amount of increase in what sort of computing power is available to break those codes, and certain classes of those codes will be broken. So when quantum computing becomes reality, right now it's still in very early stages. Very far away. Not impossible, but very far away. We're safe now. However, there are quantum resistant encryption methods that don't rely on things that would be exploited by quantum computing, which are already exist, are already in practice. So, for example, Starkware is an L2, and they use a certain kind of commitment system. I'm getting a little bit more technical, but essentially they are quantum resistant. So the encryption system that they use to validate their zero knowledge proofs relies on a certain commitment scheme, which it would not be broken by encryption. But essentially, So quantum computing breaks a significant amount of encryption, but doesn't break all kinds of encryption. And there's a lot of research done around quantum computing resistance for crypto, but also in the general world, because I promise you, if there's a production level of quantum computing, your crypto is probably going to be the least of your concerns, because there will be, massive, societal issues. Just joking. Okay, I've been talking a long time, Richard. I've just been yodeling on, really
Yeah.
talking quite a lot.
So yeah, I do have some questions for you as we go through the workshop itself.
Yeah, for
but I'm going to
sure.
save those until they're applicable.
Wonderful. That sounds great.
Just curious in the chat, if you have not ever created a wallet, can you just give me a +1 in there? I'm just curious if we need to walk through like creating a MetaMask wallet or not. So if you have never touched MetaMask or created a wallet, you don't know what a wallet is other than the thing in your pocket that you carry cash and cards in, like give me a +1 in the chat. If I don't see any, I'm going to skip the MetaMask piece. We'll give it just a minute though.
Sounds good. And I'm just going to share a link for Ben to share in the chat here.
Okay, I'm not seeing anybody talking about that.
Okay.
I am going to share my screen and talk about a couple of things really quick. I'll wait for Ben to toss my screen up on.
Sorry about that.
Thing. Turn up my volume. I'll just turn it up manually with the voice. Is this better? Maybe. I don't know. I can turn my gain up a little bit too. So if you haven't ever installed a wallet, MetaMask is probably the most used wallet in the space. So if you go to metamask.io, download it. It's a plugin for your browser. It'll walk you through all the steps. Assuming everybody has one, because nobody tossed a +1 in the chat. I will talk about chainless.org really quick. This is where I go to add chains to my wallet. So if you had a new wallet and you had never touched zkSync before.
Although I have to say, we are actually in the recommended networks for MetaMask as well. Yeah. I believe the testnet one is too, but let's definitely keep Chainless open just in case, because it's always good to have and it's a great resourse. Yeah, for sure. Why don't you do this one and then I'll share my screen I'll try the other one because I haven't set up MetaMask on mine yet. So yeah.
Well, I'll just go ahead and install MetaMask. We'll check it out real quick. And for everybody watching at home, I'm about to do something that you never actually no, I don't think I have to show my keys at all in this because I can just not back it up.
Yeah, right. I think Era is a default one, but not testnet. Thank you, Larry. Yeah, I think you're right on that one, Richard. So
yeah, the testnets, they're very limited on their testnets.
They're very limited.
Yeah, so they just have these two. So if you have a new MetaMask like this, you can just go connect your wallet. This probably isn't working because I didn't have MetaMask installed. And then you can add it to MetaMask. And that will install the network for you. Maybe, man, come on MetaMask, got it. And now we can switch to the Sepolia test network for zkSync.
Right.
So yeah. The other thing when you're setting up your wallet is you'll notice, oh no, we have no monies. On test networks, if you're not familiar with using a test network, it's basically just like a real network, but all the money is monopoly money and nothing matters on a test network. It's for testing purposes. So if you go to a faucet like this one, this learnweb3.io/faucets, go to the zkSync Sepolia faucet. You can put your address in here and get some testnet funds there. This does require you to sign in with GitHub as well. If you don't want to do that, if you put your wallet address, if you need funds in the chat, we'll do our best to kind of toss a little bit of funds your way so that you can follow along,
right,
if you'd like
to.
Yeah,
absolutely. Yeah, because I think there's a you have to connect here with GitHub, I think. Although,
right.
Did you okay, yeah. So if folks want to put their addresses, MetaMask addresses, not your private keys, just your public address.
Yeah, so your public address.
We're happy to fill this
skipping
in
ahead here.
while yeah, you're here for the testnet ETH.
So just
the test ETH.
this address here, that's what we're talking about.
That address right there. If you want, and again, this is zkSync testnet ETH, and so this is essentially Sepolia ETH, which has been migrated over for our testnet. So you know, zkSync Sepolia essentially is a good way to think about it. But it looks like everybody's good.
Yeah, I think everybody's good from there. Did you want to walk through deploying their first smart contract? Do you want me to do that? And you kind of talk us through it? Okay.
Yeah. Why don't I do that, and then I'll throw it over to you to do that. Give me 1 second just to grab contract code
screens too when he shares it.
Yeah, let me
So you had mentioned, and I saw there was a question in the chat about Remix. I think that we're going to be using a tool called Atlas, which is very similar to Remix. And this is my first question for you. So Remix compiles things for Ethereum.
Yeah.
But their compiler is slightly different if you're going to zkSync.
Right.
Why is that?
Yeah, it's a good question. Let me actually, so I'll share my screen while we're talking. Presents, share screen, alrighty. How do I manually add to MetaMask? Okay, so I would actually recommend doing the chain list approach that Richard did. All right, let's see here. Windows, MetaMask. Okay, here we go. Alrighty, so this is my, yep, okay, great. You can see that. Awesome. So again, I did exactly what Richard did, which is right before this call, I set up this is a brand new MetaMask wallet, and Richard and I, do this for our job. So we typically will do this. You should never really do a live stream with your wallet, just as for example. So this is a throwaway wallet that after this recording, I will destroy. So this is poor security form, but we're doing it for the sake of teaching the process, just FYI. Okay, so Larry says, how do I add to MetaMask? And you want to do to chainlist.org and do zkSync testnet. And yeah, you want to avoid manually adding to MetaMask. It's sort of tedious, and it's just not as clean as Chainlist. So that's really your best bet. If you really want to add it manually, you can go to docs.zkSync.io, and then if you go to the quick start, there's an add network, and you can get the details there if you really want to be super sure about the details, or if you want to add a different block explorer or something like that. So Richard, you asked about Remix and about the compiler.
Right.
And specifically, someone asked earlier about what's the difference between L2s, sidechains, and EVM. And I think this is the EVM part of that. We covered L2s and sidechains, and now we can talk about EVMs. So essentially, the short answer is that the kind of cryptography that's required for zero knowledge proofs it's a little bit like a square peg in a round hole compared to Ethereum. For a number of different reasons, when Ethereum was being built and they were building the Solidity compiler, building the Solidity language, and then to compile down to EVM bytecode, there just are certain things that just don't match up very well with the kind of math that needs to happen on ZK networks. And so certain people have taken different approaches, and different networks have taken different approaches for how to address that gap. The approach that we've taken is by switching out our compiler. So rather than using the Solidity compiler, which is the standard for networks like Linea and Scroll and Polygon ZK-AVM, we actually use our own compiler, and it's part of the LLVM compiler tool chain. And we don't have to get into this that much, but essentially, we are like a Rust-based organization. We use a lot of all our circuits are written in Rust. Our provers are written in Rust. Our network details are built out in Rust. It's very fast, very very secure language, and it's very performant. And so we want to, so essentially we've built a compiler that takes in EVM bytecode and then spits out the equivalent ZK. Well, let's call it the zkSync bytecode, essentially, so that you can use tools that you're familiar with, such as Hardhat, Foundry, Remix, and Atlas. And with some tweaks, they're a little bit, they are better. I do have to admit that, particularly for something like Remix, we're having a big overhaul of Hardhat and Foundry, so it'll be a little bit different. But it is a bit different workflow. But the promise is that there are a lot of things that are built into the EVM compiler, which a lot of people don't typically use. For example, and again, this is probably more technical than we need to get into, but the EVM compiler, the latest versions of Solidity have incorporated safe math overflow protection by default, essentially. And so even if you're compiling your code and there's no error, there's no issues of overflow, it's that those protections still kind of get wrapped up in your code. So it kind of creates bulkier, heavier, quote unquote, less performant code. So we run our own version of the Solidity compiler. We've built it through the LLVM compiler toolchain. And so some things work a little bit differently. The hope is that, we're working forever, as hard as we can to make the developer experience as seamless as possible. And we really, really think it's worth the trade-off. It's obviously a huge decision to do that, just in terms of the community, but we have found that developers can adapt really easily to it. They understand the differences, and given the sort of the state of the network, it is worth the zkSync network. It's worth the trade-off. So that's why it looks a little bit different. And so for Remix, for example, you need to use a plugin.
Right.
We're going to be showing Atlas, which is a less commonly used one, IDE. But then I think also, Richard, you're going to be using Hardhat to deploy your the Chainlink price feed, perhaps.
Yeah, no,
maybe not.
We'll stay in Atlas for it.
Stay in Atlas. Okay,
Yeah.
got it. Great, wonderful. All right, so just really quick, so everybody has, I'm assuming everybody has added Sepolia. Who wants to add Sepolia? I believe I sent myself a little bit of Sepolia ETH here. So if people want some, I got it. Just, you got to give us an address. Got to give us an address. And then if you Google Atlas IDE zkSync, there's a specific zk IDE, which is actually not this one. Give me 1 second here. Here we go. Here's Atlas. Maybe it is this one. Here we go. And it's a little bit simpler than the Remix interface. I find it's easier if you go to network over here and you do local VM. We have all kinds of great options here. We got Ethereum mainnet. We got Sepolia. We have Arbitrum, Sepolia, zkSync. Here we are. So if we go to Sepolia testnet, and then it's going to send us to this zkSync.atlaszk.ide or /IDE. And again, this is a lighter form. So like Remix would have a lot of contracts here that we do not have contracts. And we're just going to do the good old fashioned hello world. And they give us this nice populated one here. And I'm just going to grab this function here. I want to get rid of this extra bracket here. And this is should be familiar to folks as print function in hello world. It's really common. We can do a different name though here. Does anybody want to do something different? And yeah, someone's asking about Foundry rather than Hardhat. You can check out the docs right now. Next week, we're going to have a really cool version of Foundry that's going to have a big overhaul. That'll be ready next week. So if we do here, Atlas VM, it's saying local VM, but we actually want to switch to our Sepolia testnet. I believe it's detecting this address here from MetaMask. And then I will just deploy right here like this. So no constructor, so we don't have to put any tabs in. I get a signature request from zkSync, and bada bing, bada boom. After a little bit of time. Yeah, go ahead, Evershed.
Something that's different with zkSync is when you're deploying, you get that signature request instead of a regular confirm this transaction.
Yeah.
Why is that?
Yeah. The way that the deployment works is because I actually need to get the exact details, but it essentially has to do with just the way that our system contracts are set up. So rather than sort of an actual transaction, it's more of a signature. But yeah.
Okay.
Alrighty. And then here we are. We have our our contract that we have deployed, and yeah, it's that easy. It's really simple. This is Solidity. Solidity gets compiled, gets deployed. We're on a test net. The same code could then be deployed onto Ethereum, Sepolia. If we add that there, this also compiles. I need to get some Sepolia here, but you get this. And so that's it. That's the deploying on zkSync. Check out the docs for more, docs.zkSync.io. And then I'll hand it over to you, Richard, to do the price feed deployment.
Yeah, thanks. So I'm gonna use you as a proxy for the chat here with a couple of questions real quick.
Please.
So you talked about zkVMs, you talked about blockchains in general, all their benefits. You talked about like how zero knowledge stuff works, about rollups. One thing I think you kind of touched on like on the side a little bit is that, blockchains are made up of a bunch of different nodes that are all coming to consensus, right? And I'm assuming zkSync works the same way. We have a bunch of different nodes that like end up reaching consensus. Consensus is tricky in the blockchain environment though. Normally, and like I'll ask the chat too, but I'm going to use you because you'll be faster than the chat.
Yeah.
So you and I are nodes in a blockchain, right? And
yes.
You mentioned you're on the East Coast. So I'm asking you a question, not a trick question. And chat, feel free to answer this question as well. We'll all pretend we're part of this blockchain. We're all part of the zk sync here. What's 1 + 1?
2.
2. I agree. It's 2. We'll wait for the chat to come back. There's a delay, I'm sure. But I think that we agree it's 2. And I'm really hopeful the chat agrees it's 2 as well. It's not a trick question, like integer 1 + integer 1. No tricks about it. That's an easy question. That's a deterministic question, right? Easy to come up with that answer. Yeah, I'm starting to see a couple people.
Lightning speed. Lightning speed
fantastic.
here. 2.0.
We got it. We reached consensus. We did the thing. We're a blockchain. We're happy. Harder question now. What's the current temperature?
In what climate? Where you are, where I am.
I mean where you are right now. Like, what's the current temperature? You can.
Oh gosh, I can't even. I gotta go stick my hand outside.
57 degrees Fahrenheit right here.
I'd guess maybe 62 degrees Fahrenheit 62. Over here. Kind of close, actually.
2 of us are having problems reaching consensus now, right? Like,
yes, this is terrible.
It's another good question. This is a non-deterministic question, right? It depends. It depends on when I ask you this question, not just where you are when I ask you this question. Because if I ask you at midnight, it's probably gonna be different than right now.
True.
Blockchains have problems with this. Like, doesn't matter what kind of blockchain we're talking about. Like, non-deterministic questions are difficult. So this is where Chainlink comes in. So this bringing like off-chain real-world data that's non-deterministic on-chain is referred to as the Oracle problem. And so Chainlink provides a distributed Oracle network, or DON. So there's a bunch of different oracles that all reach consensus. Now you might be wondering, how did the oracles reach consensus, right? Well, if we take that same question of what's the temperature, it doesn't make sense like in a global scale, like what we're talking about here. I'll just use my house as an example. I live in a 2-story house. Often the upstairs is slightly warmer than the downstairs, right? But it makes sense to ask the question, what's the temperature in my house right now? If I had multiple sensors, they still couldn't reach consensus. But if I said, given all these different sensors inputs, put those in an array, what's the median value of an array? Now we have a question that's taken a non-deterministic question and made it deterministic, right? So say, given this array of values, what's the median value? That's going to give me the temperature in my house. And it's a way that a blockchain can agree on it because it's using the median of that array. So this is like how I like to think about how Chainlink works, right? So we have the Oracle nodes. They all come back with their answer to like what's temperature, or in the case of what we're going to be looking at, what's the price of an asset. And there will be slightly different answers to that, right? It depends on what exchange you're looking at. It depends on exactly when you look at that question. But then they all give their answers back to a contract that aggregates those answers together and comes back with the median price as the answer. So this is essentially what Chainlink does in this space, right? It gives you access to that off-chain real-world data. So what does this look like when we're talking about actually using this in a contract? And probably the easiest place to get started is the documentation. I don't know, Ben, if you want to pop my screen back up there. So if you go to docs.chain.link, let's go from the start here. We have a bunch of different products right now on zkSync. We just have data feeds. So if we take a look at data feeds, you can read about data feeds, what they are, how to use them. If you go to getting started, there's a little explainer here and then some sample code. The sample code is awesome. You can open it in Remix right here, but we're just going to copy this code and paste it into Atlas just to make sure everything was super nice and easy and consistent with what we just did. So I'll just copy all this code out. I'll go over to Atlas. I already pasted it in once, but we'll paste it in again. So we have here our contract. It's a little bit more involved in that Hello World contract that we did just a second ago, right? It's more than like 2 lines, but we can walk through this and explain it. So we've got our compiler version up here. We import this aggregator interface from the Chainlink contracts. So in Solidity, what this is doing is saying, hey, we've got another contract and it's got all this other good stuff in it. We're just going to use that here as well, right? It's basically saving us a lot of work. It's like if you're familiar with any sort of imports in programming, it's the same thing. We're basically just bringing in some other code. We have our contract here. We're calling it data consumer v3. We're setting up our aggregator interface. And we're calling it data feed. And then in our constructor, which the constructors run when we actually deploy this contract, we're setting an address for this aggregator interface. And this address is hard-coded in here. And you'll notice in this little comment up here, it's talking about Sepolia, and it's for Bitcoin USD. So our docs are going to be based on Sepolia, but we can change this to work with zkSync as well. It's going to be a different address though. So where do we go to find that information? If we head back to the documentation and we were here getting started, we went down to feed addresses and looked at price feed addresses here. If we go to networks, you can see we've got a bunch of different networks to select from here. We're looking at zkSync. So we'll click on that and then we'll go down to the zkSync Sepolia testnet and we can pick any of these. Coogan, is there one that you want us to look at today? Bitcoin, ETH, DAI?
Why don't we do Link?
Link?
Why don't we do Link, right?
We'll take a look at Link. We'll see what the value of Link is in terms of USD. So we'll copy this address. We'll come back to Atlas. We'll just take this value and we'll replace it with the address that we had. And then that's all we got to do. We have a function called get Chainlink data feed latest answer. So this function is what we'll actually be calling to get that value back. It has a bunch of stuff in here that we don't care about. We just care about answer, which is going to be that value. And so we'll get that from the latest round data and we'll return that. So let's
can we do like a you get it from the smart contract and then the chat tells us, because I imagine some friends in the chat are watching that Link price. Can we do another race like our 1+1 and then
it's
see
possible.
who's right?
Yeah, we can see.
All right. We'll see. Get ready, friends.
And I've got all this done. We'll click deploy. It's tricky though, is because like this automatically will run the function when I deploy it. So it's going to be there as soon as it deploys. So you're going to have to be fast.
All right. So yeah, very fast, chat.
So
get ready.
Deploy.
Now. Oh, sorry. Not
I'll
yet.
click sign.
Now.
And we have our price back.
Is that in Gwei though? Is that the?
So yeah, this price is like massive, right? Like that's a
huge.
big price.
Look at that.
That's huge. Yeah, somebody's coming back with like $18, and this is like I don't even know how many. So, question for you and the chat: somebody's pointing at like 18.76, 19.76, right? There's a decimal in there. What does Solidity have a big problem with in numbers?
Come on, chat. You got this. Floating point.
Decimals, right?
Decimals.
So this is actually, in order to maintain precision, this number is inflated by, I think it's 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's raised by 10 to the 8th power. So the actual value that's coming back is 1971, 72 if we round and change.
There we go. Yeah. There we go. So, looks like Tito was our winner.
Yeah, I mean, closest without going over.
Right? Yeah. Price is right
rules
for sure.
Yeah.
Price is right rules.
So yeah, so this is bringing that information on chain. You saw in the testnet There's only a couple different values, but when we start looking at mainnet, we have some more. But yeah, and there's always more coming. People are always asking, like, when is this coming to this chain, and when are we getting more information? My answer is always soon. TM.
Soon.
Right? Like, there's always more coming. We're always building out more things. But yeah, so that is the basic contract there. So we got this straight from the documentation. We just copy pasted. The best way to do coding is to copy paste, sometimes from Stack Overflow, sometimes from documentation. And I guess more frequently now it's from ChatGPT.
I was going to say, yeah, or Copilot.
I need to update my jokes. But yeah, I'll have to give some feedback to ChatGPT about that joke and how it didn't write a good one for me. But anyways, yeah, that's how data feeds works. That's what Chainlink is. Something too that people often will ask is like, well, can't I just put an Oracle node like in my office here and bring data on chain? And the answer to that question is you absolutely can. You will take all of the distributed trustless goodness of the blockchain and centralize it onto your Oracle node, which seems, maybe not the best.
It's bad.
Yeah,
bad, friends.
But you can do it. You probably shouldn't.
Sure, one could.
Yeah. But yeah, I don't know. Any questions, thoughts, comments while y'all have us here? That was my little song and dance about Chainlink.
Wonderful.
How do you connect to a feed external to the blockchain? So when it comes to connecting, I'm assuming what you mean is like, how do I get another feed in here? When it comes to these data feeds, so the Oracle nodes, they will actually be setting up these data feeds. Like they work together to put this information on chain. So this is a bit more like heavy process for data feeds. When it comes to other products that we have, like Chainlink Functions, which unfortunately isn't on zkSync yet, Chainlink Functions will let you run JavaScript from your smart contract so that you can like do computations, but also hit any API that you want. So you can bring any data that you want on chain with something like Chainlink Functions. It's just not on zkSync just yet.
Soon.
Yeah, soon TM. And I don't know why the TM makes me laugh. How is the value the contract produces returned and used? So yeah, so the aggregator contract takes all those different values from the oracles. It might make more sense if I go to, let me just take a look here really quick. I'm just gonna use one of these just to kind of illustrate. So in this Oracle, we have all these different Oracle nodes, right? And they're run by different people. They're all like unique individual people running their own nodes. They're all reporting, well, in this case, everybody's reporting the exact same thing. I probably picked a bad example. Where's it?
Maybe ETH-USD? Maybe get a little more variation with I don't know. Is there a search? Everything's like so blown up on here. Oh, interesting. Yeah, we'll try one of these. This is interesting. I didn't know you could do. Will zkSync come to CCIP soon? I hope we do. Here you see some variation, right? Like we're very close, but there is some variation between these. So all these different Oracle nodes, they're reporting their answer to that question of what's the value of this asset pair. And then the aggregator contract is then running that calculation based on the set of inputs, right? So like given this set that you see right here, what's the median value? That's something that we can calculate. Yeah, any other questions, comments, thoughts? Anything from you, Coogan? No, I'm good. No, thanks everybody for having us. Great session. Yeah, this has been great. We'll give it another minute or two, see if anybody pops in with a question at the last minute. Coming in hot. If not, Coogan, it's been a pleasure. And it was educational for me. Like, man, you covered so much stuff. I appreciate it so much. Thank you. Thank you, Richard. Thanks to Chainlink team for having us. We're so excited to collaborate with y'all and friends. Build on zkSync, docs.zkSync.io. Appreciate y'all in the chat. It's always fun having a good chat while you're doing a stream. Nothing better. For sure. The chat was awesome. All. Very, very interactive. All right. Well, thanks, everybody. Cheers.